In this video, we're going to talk about bitwise operators. Personally, throughout my career, I have never used bitwise operators. And I would also recommend you not to give full focus on this topic as it's not worth it. But if you're a student, maybe this will be helpful for your academics or for cracking interviews. So basically, all the other operators we have seen so far deal with variable, but in here we deal with the binary representation of numerical. For example, bitwise operators does not perform operation on 65, but rather it performs operations on its binary representation. The binary representation of value 65 in 32-bit format is this, and for -30 it's this. To better explain each and every bitwise operator, I might need to use annotations. Let's go there. Alright. We have unary bitwise complement, and the operator looks something like this. All this does is it will invert the bits. For example, 0 will become 1 and 1s will become 0. When we're trying to find unary bitwise complement of A, this is what the result would be. And when we convert this to a decimal value, we would get -66. Zeros have become 1 and ones have become zeros. That's it, as simple as that. We have bitwise AND operator. For this, we need to follow a table. Here it is. We have only 4 possible combinations of 0 and 1. When it comes to bitwise AND, 0 0 will become 0, 0 1 will become 0, 1 0 will become 0, and 1 1 will become 1. So the only case we would see the result as 1 is when both are 1. So what we're trying to do here is we're trying to find bitwise AND of A and B. So 1 0 will become 0, 0 1 will become 0, 0 0 will become 0, again 0, it's 0, 0, and we have 1 and 1 here, and that will make 1. Similarly, if you fill out all the bits in here, this is the output that we get, and when we convert that to a decimal value, would get 64. We have bitwise OR operator, and the operator looks something like this. We're trying to find the bitwise OR of A and B. When it comes to bitwise OR, there are 3 cases where we would get the value 1. If at least one of these 2 is 1, then the result will be 1. So 0 0 will become 0, 0 1 1, 1 0 would become 1, 1 1 will become 1. And if you calculate the bitwise OR of these 2 binary representations, this is what we get. And when we convert that to a decimal value, we would get -29. Cool. And then we have bitwise exclusive OR. In here, there are only 2 cases where we'd get the value 1. 0 0 will become 0, 0 1 will become 1, 1 0 will become 1, and 1 1 will become 0. And if you perform exclusive OR on these 2, you would get this result. And that when converted to decimal would get -93. And we have sign to left shift operator. So what this essentially does is it's going to push, since we're doing a left shift by 4, it's going to push these digits towards left side 4 times. So what that would result in is all these 4 bits will fall and we get 4 empty places here, and those will be filled with zeros. That's exactly what we have here. And when you convert that to decimal would get minus 480. We have signed right shift operator. This is similar to signed left shift operator, except it's going to push the digits towards right. In here, we're trying to push two places on the variable b. So what this is doing is it's going to push these bits towards right a couple of times. So these two would spill over and will disappear, and we get two empty locations here. And those empty locations will be filled with whatever is there in the most significant bit. So in this case it's 1. And that's exactly what we have here. And we have unsigned right shift. This will do exactly what signed right shift would do, except instead of filling the empty bits with the most significant bit, it will simply fill with zeros. So that would result in this value. If you run this program, these are the outputs that you're going to see. Go ahead and run it.